All right, everybody, and welcome to another video. So in this video, I'm going to discuss conic sections. Yes. Uh, Looking at different how shapes are formulated using different slices from a two-sided cone. So a circle, well, a circle is formed by taking one of the parallel slice uh, of a plane, and we're going to cut a plane that is parallel to one of the sides of the cone. So in this case, a circle is formulated if this plane is parallel to this side of the two-sided cone. If the plane has a slant, but it still cuts one of the bottom sides, in this case, the bottom sides of the cone, you'll get an ellipse, right? So you'll get an ellipse. A parabola is where you have the plane that's parallel to one of the sides, one of the sides of the one-sided cone. So um, this could be parallel to on the right side of the bottom side of the cone. And you'll get a parabola. And a hyperbola is where the plane is sliced on a two-sided cone, but it's at a uh, a, a straight and along vertical cut, right? So you'll get these two hyperbolas here. So here and then there, right? So those are the three, I'll say, conic sections that we'll look at. The circle is an ellipse, but the radii is constant, right? An ellipse, you'll have a vertical and a horizontal radius to look at. So first, let's look at the first type of conic section, and that is the parabola. So the parabola. Very common shape, right? This is the what the illustration of a parabola will look like in terms of the conic section, right? So the equation of this type of parabola, where it opens up or down, well, it's indicated by this equation here. Nah, I don't like that color. This equation right here. The x is squared, right? So equals 4 times p times y. And I should also point out that the center of these parabolas will be at the origin, right? The center being the vertex, right? The vertex of the parabola is at the origin, 0, 0. Okay. What a parabola is, a parabola by definition is a set of points that are equidistant to a focus, which is a point on a graph, and a what's called directrix. And this is a line, right? This here is a line. Let me write that out more clearly. So this is a line here, right? So in this illustration, so if I zoom in here, this distance between, this is the focus, right? This is the focus, right? So the distance between this focus and any point on the parabola, well, this distance will equal to this distance right here. This is the distance between the point on the parabola and then the directrix. So this line right here is what's called the directrix. Directrix. Now, in terms of this conic section, right, the focus will always be at a point 0p, okay? And the directrix is at a line, namely y equals minus p, right? And it's so these will be the two illustrations of the parabola. If it opens up or down. So if it opens up, that is where this p value here is bigger than 0, right? So the p value here, if it's bigger than 0, it's the graph of the parabola opens upward. If the p is less than 0, on the other hand, that's where the parabola is going to open downwards, right? Okay, that's when it opens downwards. Okay, so this is one type of how a parabola will be illustrated, right? And it's using this equation here. And there's also the other type, right? The other type of parabolas is where if it opens left or right. And the equation for this parabola, is going to equal to the following. It's going to be the following. So x y squared is going to equal to 4 times px, right? The focus and the directrix will be essentially flipped, right? The x and y coordinates of the focus will be flipped. So it'll be p0 here, and then the directrix will be a vertical line. So at x equals minus p, right? X equals minus p. Okay, so the parabola will open to the right if the p value is bigger than 0, and the parabola will open to the left if the p value is less than 0. Okay, so let's look at an example on how we would draw, I should say, illustrate a parabola. So let's say we have this example. So graph ay equals to 3 times x squared, so minus 3x squared. Okay, so suppose we have this example, ay equals minus 3x squared, right? So first of all, we want to formulate this equation as the conic section definition of the parabola, right? So we know that the x quantity is squared, so that means the parabola is either going to open to the right or it's going to open to the left, right? And another indicator is, well, we have a negative quantity here. So the parabola will open to the left, right? It's going to open to the left. Okay, so two things we were given for free, essentially, right? So what we want to do is we want to formulate this equation that will look like this. X squared equals to 4 times p times times y. 4 times p times y, right? So if we solve for x squared here, what we will get is that, so we'll have x squared is equal to negative 8/3 times y. Okay. So so the other part of this question is to find the focus and the directrix. All right. And then from here, we'll be able to draw out precisely what a rough sketch of this parabola here, right? So what we know is that it opens to the left uh and the x is squared, right? So the thing we want to look at is we want to solve for the p value, right? So what we want to do is we want to solve p for which 4 times p is equal to -8/3, right? So that's what we're going to do. 4 times p equals -8/3, right? That was the coefficient on y, right? So p is equal to, I believe, -2/3, right? So p is equal to -2/3. Okay. So, so we know that the focus, since the x quantity is squared, so the focus will be 0, -2/3, 0p, and then the directrix, I'll label out that as d, that is going to equal to, that's going to be, I should say, y is equal to 2/3, right? Y equals 2/3. So our graph, if I just do it here, yeah. So here's my graph. Okay, so x and then y. All right. And so what we want to do is label out the directrix as a horizontal line, which is here. So I'll say this is y equals 2/3. That's the directrix. And the vertex is at the origin, right? So we're going to start off here. Okay. And what we want to do is look at or plot out the directrix, right? So this should be the same distance. So I'll say this is the focus right here. So this is the focus. And then you can sketch out roughly what this graph will look like, right? So so okay, I'm just looking at different notable points I can label out. So if y is -3, x is plus or minus 2√2. So -2√2 and then -3, and then over here. I should say positive. Okay. So that's another thing you can do, right? So just verify like which points are on the parabola. So that's a sketch, what a parabola looks like. Okay. And this actually is pretty useful in making satellite dishes, right? Because parabolas, three-dimensional ones, have this property that that reflects with light or any other signal that is reflected off a receiver on a reflector on a satellite dish, right? So if a particle is approaching on a line that's parallel to the axis of the parabola, so the axis of like the rotation being here, right? So if it's approaching the satellite at a parallel to the axis where the satellite is pointing at, right? Um, the light will reflect off on the receiver, and that light will converge on a focal point. So it will bounce off on the reflector, and this light will, or the signal will converge on a receiver, right? And this is useful. This is a useful property for parabolas, right? Um, and reflects off on physics and all that stuff. So, yeah, so parabolas are pretty useful in that aspect, right? So let's talk about the second type of conic section, and that refers to what's called the ellipse. the ellipse. All right. Not just the lip service. Okay. Now, there's two variations of drawing out an ellipse, right? The first type, where the major axis, where the axis has a larger, I'll say, diameter, right? Um, is horizontal, right? So in that sense, this would be the equation of the ellipse if the major axis is horizontal, right? So we're supposing that the a squared quantity is bigger than the b squared quantity, right? X squared over a squared plus y squared over b squared is equal to 1, okay? And this is the illustration of what the ellipse will look like if the major axis is horizontal, right? So, um, um, so yeah, so this just trying to make sense of this. So this here, so this line right here, this is A, and this line right here is B, right? A over B. A and B. Okay. Um, so so the vertices will be the points on the ellipse that are part of the major axis, right? So the vertices in this case is at A0 and then minus A0, right? What they label as V1 and then V2 and V1 respectively, right? So they are called the vertices. The foci, on the other hand, the foci are these points, minus C0 and then C0, right? C0, okay, which are labeled F1 and F2 respectively, okay? Um, and to figure out what the C value is, we get to use this relationship, right? A squared is equal to B squared plus C squared, right? And it refers to the Pythagorean theorem, and it's talking about this right triangle that's represented in blue here, right? So it's referring to this right triangle here, but I like to think more about it as just subtracting B squared to both sides, and you'll have that C squared is equal to A squared minus B squared. Okay, since the A squared quantity is bigger. And then what's special about an ellipse is that so this distance, so if I pick any point on the boundary of the ellipse, so let's say here, right? So if I pick any point on the ellipse here, well, the distance from this point to one foci plus the distance of that point on the ellipse and the other foci, so I'll call this D1 plus D2, in absolute value, right? In absolute value, it equals to a constant. Namely, it's 2 times the A number, 2 times the major axis, right? And that's what's special about ellipses, okay? So this is where the ellipse is whose major axis is the x-axis, right? Or the horizontal axis. This is the other type, right? But this time the major axis is vertical. So the a squared quantity is in the denominator of the y squared value, right? So um, um, my examples. So Yeah, and then the vertices will be on the ellipse with respect to the major axis being the y-axis. So the vertices this time is at 0a and then 0, -a, and these will be the foci. But nevertheless, it still obtains the property where any point on the ellipse is well, the definition of the ellipse is where the distances of these values added together, absolute value d1 plus d2 is equal to 2 times a, right? So it equals to a constant, right? So yeah, so it obtains that definition, okay? So let's look at an example, right? So formulate and draw the ellipse 12x squared plus 5y squared is equal to 60. Okay. So first of all, what we want to do is this is not in the standard form of the ellipse, right? So what we want to do is we want to either express this equation in terms of x squared over a squared plus y squared over b squared equals 1, or something like this, right? Y squared over a squared plus x squared over b squared is equal to 1, right? Either one of these forms we need to express, right? So if I divide both sides by 60, right? So I'll have so x squared over 5 plus y squared over 12 equals 1, right? So our whole point is to get this right-hand side over here to equal to 1, right? So that's the important thing. Okay. So now we know that since 12 is bigger than 5, right? 12 is going to be a squared. So a squared is 12, and then b squared is equal to 5. And so that means the major axis is vertical. It's a vertical axis, right? So, okay. So right here, we need to figure out what a and b equal to. So we know that, so if we square root both sides on these equations, we have that a is equal to the square root of 12, and then b is equal to the square root of 5, right? Square root of 5 is a little bit bigger than 2, right? So here, and then square root of 12, that is square root of 3 times 2 times 2. So 2 root 3. 2 root 3. Okay. So these will be our vertices. So the vertices, so V1, this will be at 2 root shoot. This would be at 2 root 3, 0. And then the other vertex is at, shoot, I did it again. Did a mistake. 2 root 3. And then V2, 0 minus 2 root 3, right? And so these points will be root minus root 5, 0. Minus root 5, 0, and then root 5, and then 0, right? It's just a rough looking ellipse here, right? Okay. And also what we need to do is figure out the foci, right? The foci is generated if C, the foci are points, in this case, C0 and then minus C0, where C squared is equal to A squared minus B squared, right? So C squared, that was equal to 12 minus 5, right? And so C squared is equal to 7. Okay. And so to figure out what C is equal to the square root of 7, right? And so we just disregard the negative root because the point that we're interested in, the points that we are interested in is C0 and minus C0. Okay. I'm sorry. Since it's vertical, these are flipped. So 0 minus C and then 0C. Okay. So, yeah, root 7 is right here and then right here, right? So one of the foci is 0 root 7, and then the other foci is 0 minus root 7, okay? And that's it in terms of figuring out and formulating the equation of the ellipse, right? And ellipses are useful in astronomy, right? Kepler. How do you spell his name? Johannes Kepler's. So this refers to Kepler's first law of planetary motion. So Kepler's law of planetary motion. Right. I think one of the first laws was planetary bodies orbit in an ellipsoidal pattern, right? And I believe the third law of planetary motion determines the foci, I guess. So yeah, so it's pretty useful in ellipses are useful in astronomy. So okay, last but not least is the equations of the hyperbola. So, okay, so this is the illustration and the in the equations of the hyperbola. So what's going to be interesting about these this Conic section here is well, they're going to generate asymptotes. And the foci, it's going to be a point that is outside of the parabola, right? So they are inverted ellipses, essentially, right? So, okay, so this is one form of the hyperbola where the major axis, or they call this the transverse axis, excuse me, is horizontal, right? And this is the straightforward equation of the hyperbola. X squared over a squared minus y squared over b squared is 1. Since the y squared is negative, we want the hyperbola to be symmetric uh, with the x-axis, right? So the y portion could yeah, so you want the hyperbola to be transversing with the x-axis, right? And then the vertices on the parabola will be a0, excuse me, and then minus a0, right? Okay. And then to figure out the foci, just use b squared is equal to c squared minus a squared, or just solve this equation, a squared plus b squared. Okay. Okay. So, um, yeah. So what's great about this, about hyperbolas is the definition is this distance here plus this distance here will equal to a constant. Okay. It always equals to a constant. And so also the asymptotes that I mentioned before is that y equals minus b over ax, and then y is equal to b over ax. So plus or minus b over ax equals y would be your asymptotes. Okay. And so this is where, so this hyperbola here is where the transverse is or the major axis is horizontal. Okay. And this is the other type right here. Okay. The major axis is vertical. Y squared over a squared minus x squared over b squared is equal to 1. Similarly, this is how you would solve for the foci, a squared plus b squared, right? And um, and so these are the vertices, and then the foci are these points here on the outside. And the asymptotes this time, it's y is equal to plus or minus a over bx. Okay. So let me go over one example on how to draw the uh, hyperbola. Okay. So let's see, where is one? Oh, this one here. So so the hyperbola defined by this equation. 25y squared minus 4x squared equals 100. Okay. So what we want to do is we want to get this right side equal to 1, right? And the way to do this is divide both sides by 100, right? So if I divide both sides of this equation by 100, I will get, so y squared over 4 minus x squared over 25, that equals to 1, right? equals to null. Do you know how this hyperbola is going to open? Is it going to open like this, or is it going to open like this? Well, the x squared quantity is negative, right? So the x squared quantity here is negative. So that means it's going to open up and then down, right? It's going to open up and then down. So, okay, so we get that. So we get those pieces of information for free. So, so if I go like this, and I'll draw out this hyperbola over here. Right over here. Okay. So, so the first thing we want to do is the hyperbola is it won't be within a box, right? So if you look at these illustrations, you can see like how they're opening, right? So the way to draw out the hyperbola is to construct a box, right? First. So our center is at the origin, right? Okay, so we want to start off here, and then we want to label out what the length of the width and the width of this box would be. So to determine the length and the width of this box is using these bottom numbers here, right? So in this case, how it's formulated, so the a squared is 4, and then the b squared is 25, right? So if I square root both sides, I'll get a is 2 and then b is 5, right? So, but be careful. I like to view this as how you would look at slope. Slope is rise over run. The x value is the run number, and the y value is the rise number, right? So, so we want to go up by 5, right? Oops. So we want to go up by 5 units, right? And then we want to go 2 units in the x direction. So this is when a is 2. So here's a, and then b is here, right? And so we want to draw in 2 units. Maybe I should 2, 3, 4, 5 here, then 1, 2, and then 1, 2 here. Five, 2, 2, and then here. So this is your box, right? So this length here is where a is 2, b is 5, right? And so the next thing we want to do is draw in our asymptotes, right? Our asymptotes will look like this. Oops. So our asymptotes will look something like this. So you want to connect lines along the diagonal of the box. So, shoot. Okay. So these are straight lines here. And then these asymptotes, well, it's going to be y is equal to 5/2 x. That's for the right, for the first one here on the right, and then the other one is just minus 5/2 x. So these are your asymptotes. Okay. Now the thing that we need to do is draw in our, well, that's the last thing we need. Yeah. The next thing we're gonna do is we're gonna draw in our hyperbola. So it opens up and down, so it opens like this, right? And it opens downward like this. Okay. So that's the actual hyperbola. The last thing we need to do is compute the foci, right? The foci, right? Okay. So to compute the foci, it's equal. So this would be the equation for the foci. C squared is equal to A squared plus B squared. We know that the C number, I'm sorry, the B squared number is 25 and the A squared number is 4, right? So 25 plus 4, and so C squared is 29, right? So, so that means the foci will be, so if I just extend these lines out further, one foci will be here. And one other foci, and the other foci will be down here. 0 minus the square root of 29, right? And that's pretty much how you draw in a hyperbola. Now, if you overheard of my my phone beeping, my phone just saying a few seconds ago, this is how cooling towers are formulated at nuclear power plants. So a cooling tower is a special shape called a hyperboloid. So if I were to take this hyperbola in particular and rotate it about the x-axis, I will generate what's called a hyperboloid of one sheet. So really, it's going to be this really big oblong hyperbola. Right? It's sort of like a coffee cup, right? Basically. Right? And how it's made, it's just releasing out steam after water is cooled for for to be used again at the power plant, right? So how it's made is just looking at the sort of a theorem behind a physics theorem on how steam is released in a cooling tower, right? So yeah, so conic sections appear anywhere, everywhere, anywhere and everywhere, right? So there's also polar section equations of conic sections in polar form, but I'll leave that out for next time. But this is a good stopping point for this section. So hopefully this helped. This is the sort of a brief overview of what conic sections are and how to formulate equations of conic sections. If you have questions, leave it in the comments. Until then, I will see you in the next video. Take care.